This video is all about solving systems using Gaussian elimination and gauss-jordan elimination. Our goal is to solve a system. That means we're looking for the collection of variables, in this case x, a y, and a z, that would solve all three equations. To begin with, we want to make sure that our system is written so that all variables line up. In the third equation, the z is in the wrong place. It should be on the left of the equal side. So I'm going to move it over to be plus z. Then I have my equal signs and my constants on the right-hand side. This is the format we want. After this, we can put the matrix into what's called, the system into what's called an augmented matrix. The first column will hold the coefficients of x's, then y's, then z's. Then we use the augment line as the equal signs and the constants on the other side. So let's start with the x's. I see in my first equation there's a 1 in front of x, a 1 in front of y, a -2 in front of z, and 3 as the constant. Second equation, 2 in front of x, -1 for y, 5 for z, 0 as the constant. Last equation, -1x, 4y, +1z because we moved it over, and -21 as our constant. You'll notice that each column represents the coefficients of one of our variables, and each row represented one of our equations to begin with. Let's look at this matrix on the next slide. In our first stage, our goal is to have a 1 in the top left corner. Since we already have that 1, we can just start the process of row reducing from here. If we didn't, like let's say if these first two equations had been switched, then we would take a second first to switch those two rows, which we're allowed to do as long as we switch everything in the row with each other, and start with that 1 in the top left corner. From here, our next goal is to zero out the entries below that leading 1. The first thing I'm going to do is take row 2 and change it. I'm going to take everything in row 2 and subtract 2 times the entry above it in row 1. Then I'll have a 0 here, and I'll have to change the rest of the entries accordingly. For row 3, I'll change row 3 by adding the entries above in row 1. This will ensure a 0 appearing here. So let's do that one at a time. Let's start with the row we're not changing, which is the first row. We'll write that one out just as is. We're using that one to change the others, but it will stay the same. Let's change the second row. We want row 2 minus 2 row 1. So row 2, 2 minus 2 gives us a 0. -1 minus 2 gives us a -3. 5 plus 4 gives us 9. 0 minus 6 gives us -6. Moving to row 3. Row 3 plus row 1. So -1 plus 1 gives us 0. 4 plus 1 gives us 5. 1 plus -2 is -1. And -21 plus 3 gives us -18. Our goal now is to make our next leading one to the right and below of the last leading one that we made. To do this, we can simply take row 2 and change it by dividing every entry in row 2 by -3. This will make that red circle become a 1 as we want. So our first row and our last row won't change at all in this step. And our second row, every element will be divided by -3. So 0 over -3 stays 0. -3 over -3, there's that 1 that we want. 9 over -3 leaves us with -3. And -6 over -3 leaves us with 2. If we're doing Gaussian elimination and we want to move forward to REF, then our next goal will be to zero out the entry just below the last leading one that we've made. There's our leading one. We want to zero out the entry below it by using that leading one, so we're going to take our entries in row 3 and change them. And what we can do is row 3 minus 5 times row 2. I want to make sure I use the row with the leading one that I just created. Otherwise, I'll destroy the zeros that I took time to create before. If you're destroying zeros you've already created, you're going in the wrong direction. If we choose this row operation, we're not changing the first row or the second. And we're taking everything in the third row and subtracting 5 times what's above it in the second. So 0 minus 0 is 0. 5 minus 5 is the 0 that we wanted. Minus 1, with minus is plus, so minus 1 plus 15 gives us 14. And finally, negative 18 minus another 10 gives us negative 28. Next goal is to make our last leading one in the most bottom entry here on the right. So we can just take that last row and we can divide it by 14. Which means what we'll end up with is a matrix that's in REF form, where each row begins with a leading one and each leading one has zeros to the left of it. 14 divided by 14 gives us that 1, and 28 divided by 14 with a negative gives us negative 2. From here, we can read our answer from the matrix. So here's our matrix. Remember that each column corresponded to a specific variable. So from here, if I start from the bottom, I can rewrite those equations in this new reduced form. The bottom row tells me that 0x plus 0y plus 1z equals negative 2. So in other words, there's my z variable. Z equals negative 2. Then I go to the next row. 0x plus 1y minus 3z's equal 2. But I already know what z is from above. So another way to write this is y, and then negative 3 times negative 2 gives us a plus 6 equals 2. Bring that 6 over, it becomes negative 6, and we have y equals negative 4. And then our first row, 1x plus 1y minus 2z's equal 3. But again, I already know that y should be negative 4 and z should be negative 2. So when I plug those in, I get x minus 4 plus 4 equals 3. So minus 4 plus 4, these two will cancel out. And in other words, x equals 3. And there's my solution. I've got x equals 3, y equals negative 4, and z equals minus 2. We can check that answer back up in our original equations. Remember, our solution was x equals 3, y equals negative 4, z equals negative 2. All three equations should be satisfied. So if I do 3 minus 4 plus 4, I'll get 3. If I do 6 plus 4 makes 10, and then minus 10 makes 0. Good, so I'm plugging in my x and my y and my z. Here I have negative 3 minus another 16 makes minus 19. Minus another 2 makes minus 21. So I know my answer is correct. This was solving using Gaussian elimination and reduced echelon form. Now, if we wanted to do Gauss-Jordan elimination and row-reduced echelon form, we would go back to stage 3 and proceed a little bit differently from there. So let's go back to where we left off in stage 3. So this was the matrix we had for stage 3. We had just made this leading one. And what we did next was make a 0 below it. For RREF, we also want zeros above. So we took row 3 and changed it. We did row 3 becomes row 3 minus 5 times row 2, same as before. But now we would also do something to row 1. We would make row 1 become row 1 minus row 2. Again, using that leading 1 to make the 0 above. Now our matrix would look as follows. We know what the second row looks like. We didn't change it. We know what the third row looks like because we did this last time. And our first row, we want to do row 1 minus row 2. 1 minus 0 makes 1. 1 minus 1 makes that 0 we want. Negative 2 minus minus 3, so negative 2 plus 3 makes a 1. And 3 minus 2 makes another 1 for us. Now again, we want to make the next leading 1, so we will divide that last row by 14. Let's do that in the next stage. So there's the matrix we're looking for. We're going to take row 3 and divide it by 14. So this is the same step we did in the last one when we were trying to make the leading 1 in that last row. So 0, 0, there's a 1, there's a negative 2. And now instead of stopping, we're going to do one more step where we make zeros above that final leading 1. So there's our matrix. We want zeros here, so we'll do row 1 becomes row 1 minus row 3, always using the leading 1 we just made. And row 2 becomes row 2 plus 3, row 3. So last row doesn't change. Let's do the first row. Row 1 minus row 3. 1 minus 0 stays 1. 0 minus 0 stays 0. Then 1 minus 1, there's the 0 we want. And 1 plus 2 makes 3. For our middle row, 0 plus 3 times 0 is still 0. 1 plus 3 times 0 is still 1. Minus 3 plus 3 gives us that 0 we wanted. And finally, 2 minus 6 gives us negative 4. This is a matrix in row reduced echelon form, which has zeros above and below leading 1s. The nice thing about RREF is that you don't have to do that back substitution that we did before. In RREF, we can read the answers right from the matrix. Remembering our variables, that last row tells me that exactly z equals negative 2. The second row tells me that y equals negative 4. And the first row tells me that x equals 3. The same solution either way. One involves more work with a matrix and less substitution afterwards, like this. The other version requires less work with the matrix, but more work afterwards to get the answer. What if our final matrix had looked like this? Whenever we have a column that doesn't have a leading 1 in it, we say that we're going to have infinitely many solutions. So we let that variable be a parameter or something arbitrary. Then the rest of the variables, our y and our x, would be the same. So y would still be negative 4, x would still be 3. But in this case, we would say we have infinitely many solutions instead of just one, because our z can be anything we want. What if the matrix had looked like this? Similar but slightly different. Again, starting from the bottom, if we read off what this equation's telling us, it's saying 0x plus 0y plus 0z equals negative 2. But wait a minute, 0 doesn't equal negative 2. And whenever we're solving a system and getting a false contradiction like this, that means that what we were trying to solve had no solutions at all. I hope that was helpful for you, and I will see you in the next video.